Hello everyone, welcome back. So myself Ayush Tripathi, mentor and problem setter at GeeksforGeeks, and I welcome you all to this post-analysis video of last weekly contest 166. And here I will discuss all the four solutions. And I personally categorize the first three problems from easy to a moderate level. And the last problem was a bit tricky, but don't worry, we'll discuss all the four solutions. So starting from the first problem, count minimum swap. Given a binary string and zero-base indexing has been considered of length n, and in one operation you can swap any two digits of the string, and our task is to count the minimum number of swaps or minimum number of operation required to rearrange the string such that sum of digits at even position is equal to sum of digits at odd position, and if it is not possible then we have to return -1. So let's see how we can solve this problem. So the very first and the very basic observation, we do not select both the digits from odd position, and we do not select both the digits from the even position. It does not make any sense, and the sum would remain same. So first I will find the sum of digits at odd position. Let's say sum odd. So starting from index 1, then index 3 and index 5 and index 7. Cool. So the sum is 1 for at index 1, then 0 at index 3, then 0 at index 5 and 0 at index 7, which is equal to 1. Then the sum of digits at even position, which is equal to 0. Index 0 is a even number, 0 is a even number. Then value at index 2, which is 1. And at index 4 we have 0, at index 6 we have a 1, and at index 8 we have a 1, so which is equal to 3. So the initial difference between odd sum and even sum is absolute difference of 3 and 1. So 3 minus 1 and the absolute difference, which is equal to 2. So here's the solution. If the initial difference is even, then it is possible to reduce this difference to 0, because we wanted to make the sum at odd position and the sum at even position same. That is, the difference that we want to make is 0. And if the initial difference is even, then we can make it to 0. And if it is odd, then it is not possible. And why is it so? Because after each operation the difference would reduce by 2. So here the sum of the digits, that is the total sum is constant. And if we are swapping two number, let's say we select this index 3 and index 6, and now let me just swap these values. So 0 to 1 and 1 to 0. Now the sum of digits at odd position is increased by 1, and since the total sum is constant, so the sum of digits at even position would decrease by 1. So at index 6 previously we have 1, and now we have 0. Cool. So this sum is increased by 1, and this sum is decreased by 1. So can I say this thing? Every time we are reducing the difference, by 2. Difference is equal, after the one operation, that is equal to difference minus 2. So if the initial difference is even, then it is possible to make it 0. And how many operations we require? It is very simple. Just simply initial difference. So initial difference and divided by 2. Cool. And yeah, this is my answer. And if the initial difference was odd, then it is not possible. So in that case, return -1. Otherwise, initial difference by 2, because after each operation the difference reduced by 2. So this is the complete solution. Now let me just show you the implementation here. So here I have declared two variables, even sum and odd sum, and initialize both the variables with 0. Then taken the size of the string, iterate over all the indices, and if the current index is odd, that is I and 1. If the LSP is set, then it is odd number. So if the current index is odd, then I am adding the integer 1 if the digit is 1 in my odd sum, and if it is 0, then I am adding 0. So this is a boolean expression, and if it is true, then it is 1, and if it is false, that is digit not equal to 1. So in that case, false means 0, and we are adding 0 in our variable. And yeah, this is something that we want. And if the position, that is if I is even, then we are adding the value in even some variable. And after this, I am calculating the difference, absolute difference. And if the difference is odd, then it is not possible to make it 0. So in that case, I will simply return -1. And otherwise, the number of operations that we required is a difference, initial difference by 2. After every operation, the difference reduced by 2. So that's why it is a initial difference divided by 2. So talking about the time complexity, so the time complexity is a linear because of this for loop, and the space complexity is a constant as we are not using any extra space such as array string or something. Cool. So this is the second problem, variant operation. In this problem, you are given an array of size n, and you can perform the following operation at most k time. In one operation, you can select an element I in the range from 1 to n, and one base indexing has been considered from this array A, and choose a value x which is in the range from L to R, and this L and R will be given to you, and assign value x to A of I. And our task is to count the maximum number of unique values that can be present in this array A after performing at most k operation. So let's see how we can solve this problem. And this is a greedy problem where we greedily select the best possibilities to find the final answer. So consider this array where the value of k is 3, and the value of L is 1, and the value of R is 3. And this is the array of 8 elements. So the frequency of element 2 is 2. This is another occurrence of 2. 1 has frequency 2, so another occurrence of 1. And 4 has frequency 1. 5 has frequency 1. And 3 has frequency 2. This is another occurrence of 3. So the very basic observation, we wanted to replace these duplicate elements. We want to replace these duplicate elements. All these elements are unique, so replacing them is just a waste of operation. We always replace the elements which are duplicate, and we can select any value of x in the range from L to R. And for this sample input, the value of L is 1. So what are the possibilities for x we have? So from L to R, both the values are inclusive. So 1, value of L, then 2, and 3, the value of R. And all these three elements, all the values of x is already present in this array, 1, 2, and 3. So no matter what value of x you select, what the value of I index you select, you are always replacing a of I with some element which is already present in this array. So we cannot increase the number of unique element. It would remain same, which is equal to 5. So in this case, our answer is 5. Now this is the second observation. Second sample input where the value of k is equal to 3, the value of r is equal to 4, and the value of L is equal to 4, and the value of R is equal to 6. So the possible values for x is 4, 5, and 6. And what are the duplicate element we have? 2 has frequency 3. So this is other two occurrences of 2. And 1 has frequency 1. 4 has frequency 1. 5 has frequency 1. And 3 has frequency 2. This is another occurrence of 3. So we wanted to replace these three duplicate elements. And the possible values that we have is 4, 5, and 6. So 4 is already present in this array. So we cannot select 4. And 5 also is already present, and this 6 is not present in this array. So here I can only replace one element and make it 6, and the other values are already present in this array. So let's say we selected this index and replace this value 2 with the 6. So the number of unique element after this is equal to 6. So this is another observation where there might be a case when the number of duplicate elements are greater than the number of elements in the range from L to R, which is not present in this array. So only one element is there, which is only one value of x is there, which is equal to 6, and it is not present in this array. So we can select any duplicate element and replace it with the 6. So then the next example, the value of L as 10 and the value of R as 15. So the possible values for x is from 10 to 15, 10, 11, 12, 13, and 15. These are the possible values for x that we can select. And what are the duplicate element we have? 2 has frequency 1, 1 has frequency 1, 4 has frequency 1, and 5 has frequency 1, 3 has frequency 2. This is another occurrence of 3, and 9 and 8 are also having a frequency 1. So all these elements which is from L to R are not present in this array. So we can select any element. Let's say x is equal to 10, and then we can replace this duplicate element. Replace this duplicate element with the value 10. Cool. So now the number of operation is reduced by 1. So k is equal to 2. Now all the values are unique. So we do not perform any operation, and this is the maximum number of unique element. So in this case, my answer is equal to 8, which is the size of this array, and all the elements are unique. So now let me just quickly generalize this idea. So the first step is to find the number of duplicate elements. So count a duplicate, and then the second step is to find the number of values of x which is not present in this array. So values of x in the range from L to R, and not present in array A. Cool. And now once you know the number of duplicate element, let's say it is equal to x, and let's say this value is equal to y, and we also know the value of k, initial value of k. So how many elements how many elements we can replace? So it is simply equal to minimum of k. There might be we are only allowed to perform at most k operation, and minimum of x. There might be a case when the value of k is bigger than the value of x. That is, number of duplicate element we have less than the number of operation that we can perform, and we just only want to replace x number of duplicate element, and minimum of k comma x, and comma y. Cool. So there might be a case when the number of unique element in the range from L to R is less than the value of k, and less than the number of duplicate elements. So in that case, we can only select y unique element which is not in the range, not in present in array A, and in the range from L to R. So yeah, these many operations we can perform, and these many new unique elements that we can generate. So this is the complete solution. Now let me just show you the implementation here. First, I'm getting the size of this array A, so A dot size, and then I'm sorting this array A, and then A dot erase. This erase is the method of vector class of str library, and here I am passing using this method this function unique, and basically unique from, and this is the range from where we want to remove all the duplicate elements. So just here is the parameter, and I wanted to remove all the duplicate elements. So first sort this array and remove the duplicate element. Sorting will take n log of n time, and this erase will take a linear time. Then once you have removed all the duplicate element, then again I am finding the size, that is sz is equal to a dot size. Here all the elements are unique, and the duplicate elements are got removed, and the number of duplicate elements would be initial size n, and minus current size. And once I get this thing, then I can simply check how many elements are there in the range from L to R, which is not present in this array A. So not present, and initially I will initialize this variable with the entire range from L to R, and which is R minus L plus 1, because both the values R and L are inclusive, so that's why plus 1. And then I iterate over all the elements, unique element, and if A of I is greater than or equal to L and it is less than or equal to R, that this means this current element, ith element, is in the range from L to R. So I will simply decrement this variable not present. And then how many unique element, new unique element that we can generate, it is equal to minimum of k comma duplicate comma not present. And then I will simply return size, number of unique element from the original array, and the new unique element that I can generate. Cool. So the time complexity is n log of n, this one. And the space complexity is constant since we are not using any extra space such as array string or something. Cool, got accepted. So this is the third problem, longest exclusive subarray. And in this problem, you are given an array A of size n, and a subarray is considered exclusive if the bitwise OR of the subarray results in a number that has all the bit set in its binary representation and we need to find the length of longest exclusive subarray. And an exclusive subarray must have a bitwise OR in the form of 2 power k minus 1, and the value of k is in the range from 1 to 30, as all the values a of I is less than or equal to 10 power 9. So a of I is less than or equal to 10 power 9, and exclusive subarray must have a bitwise OR in the form of 2 power k minus 1, and 2 power 30, which is greater than 10 power 9. 10 power 9. So there are only 30 possible values of bitwise or of an exclusive subarray, and let me write a few of them. So it is 1, the binary representation, and which is 2 power 1 minus 1, and then next we can have 2 power 2, 2 power 2 minus minus 1, 2 power k minus 1. So it is 1 1, the binary representation of 3, then 7, which is 3 times 1, and it is 2 power 3, which is 8, 8 minus 1. Cool. And then we have a 15, which is 2 power 4, 16, and minus 1, 2 power k minus 1 in this form, and up till 2 power 30, 2 power 30, which is actually greater than 10 power 9, and the maximum value of a of I is 10 power 9. So that's why we don't need to check after this, and minus 1. So this means 29 times 1. So 1, 1, and 29 times. So this is a constant number. These are only 30 possibilities for bitwise OR of exclusive subarray. So we can iterate over all these 30 possibilities, and we check the current bitwise OR is mask. So mask is equal to 2 power I minus 1, and here I will iterate over all the possible values of I. Here I will iterate over all the possible values of I in the range from 1 to 30. Cool. And then I will, for every mask, I will find the length of longest subarray which has bitwise or it equal to mask. So how we can find the length of longest subarray for particular mask? Mask means hiding some information inside it, which is 2 power I minus 1. So one very basic observation, that is OR is an increasing function, and bitwise operator AND is a decreasing function. So let's say you are given an element X which has some value, and what if I take a OR with Y? So this value always be greater than or equal to X, and it is also greater than or equal to Y. And why is it so? Let's say you have X with a binary representation of 1 0 1 1 and 0 0 and 1, and the value Y which has some binary representation, and I will take OR of these two values. So what is the result? So at this position I have 1. So no matter what here we have, if it is 0, then also it is 1, and if it is 1, then also it is 1. So no matter what we have at here, the result would always be equal to 1. And here we have 0, so it depends on the bit of Y. If it is 1, then it is 1, and if it is 0, then it is 0. So let's just leave at this point of time, and then this bit is 1. So no matter what here we have, it is always 1, and similarly, no matter what here we have in Y, the result would always 1. And similarly, it depends on a bit of Y. Then because here we have 0, then here also we have 0, and here it is 1. So it depends. So it does not depends on a bit of Y. No matter what we have, the result would always equal to 1. 1, 1 or 1, which is equal to 1, and 1 or 0, which is equal to also 1. Cool. So in the worst case, let's say all the values are 0. So here we have 0, and at this place we have 0, and at this place also we have 0. So 0, then these two 0, and this value is equal to X. So in the worst case it is equal to X, and it is always greater than or equal to X. If we have all the zeros at these position, then it is equal to X, and if we have something other than 0, then it is greater than X. So that's why OR is an increasing function, and AND is a decreasing function. AND is a decreasing function. You can easily prove with the same logic. Let's say Y and X and Y. So this value is always less than or equal to X. So let's say the binary representation of x, I am writing the same binary representation, and 1 0 1 1, then 0 0 and 1, and the value of y, let's say, okay, let's say it is something. So then what is the value of y and x and y? So what is this value? So at this position, at this position we have 1. So if in y we have 1, then it is 1, and if it is 0, then here we have 0. Cool. So it depends on bit of y, but here we have 0. At this position I have 0. So no matter what you have in y, the result would always be 0. The result is always 0, 0 and something which is equal to 0. And at this position we have 1, so it depends on a bit of y. If it is 1, then 1. If it is 0, then it is 0. So it depends on y, and here we have 1, so I know the result would always be equal to 0, and here also we have 0. So at these position I already know the result. But at these position it depends on y. So let's consider the best case, that is we have 1. So 1 1 and 1. So it is 1 1 1 and 1. So it is equal to x, and if we have some bit which is other than 1, it is 0, then it is less than x. So x and y is always less than or equal to x. So I hope this thing is clear to everyone. That's why and is a decreasing function. So what I'm trying to say, whenever you have some array, you have some subarray, and if you add element in that subarray, then the bitwise OR would definitely greater than or equal to the previous bitwise OR. So now let me just quickly summarize all the things and discuss the approach, the solution for this problem. So I iterate over all the possible values of mask, that is from I is equal to 1, from I is equal to 1 to 30, and the value of mask is 2 power I minus 1, and then we'll find what is the length of longest subarray which has bitwise OR, which has a bitwise OR is equal to this mask. So the idea is very simple. Start iterating from index 0. Let's say j is equal to 0, and it goes till the size of the array, and up to index n minus 1. And keep track of the current OR. And initialize it with 0. And here I will store the bitwise OR of current subarray. And we keep on adding the elements, and once we get that the value of current is equal to mask, then what I can say, every time whenever the value of current is equal to mask, so in that case I will simply update the answer. So answer is equal to the maximum subarray length of exclusive subarray. It is equal to max of answer that we have so far, and comma j plus 1. And why it is plus 1? Because of zero based indexing. And every time just simply update this thing. So current is equal to current or a of j. So this is basically a sliding window approach. And there is another case. There might be a case where, let's say, when the value of mask it is equal to 0 0 and 1 1 1. So this is equal to 2 power 4 and minus 1. This is also one valid bitwise OR of exclusive subarray. And let's say the value of a of I, the value of a of j, it is equal to 1 1 0 and 1 1 1 and 1. So in that case, if you take a OR, then it would be simply 1 and 0 and 1 1 1. So I cannot include this element. Cannot include this element in the previous subarray, and in this case we have to start a new subarray. So in this case, start new subarray. So yeah, this is the complete solution. Let me just show you the implementation here. So first I'm taking the size of this array A, and this max length method that you have to complete, initializing answer with 0, then iterating over all the possible values of bitwise OR of an exclusive subarray, and 1 to 30, 2 power 30 is greater than 10 power 9, and the maximum value of a of I is 10 power 9, then this is current mask, and the length of yeah, this here here I will keep track of the length and the value of current. Here current means the current bitwise OR, and I iterate over all the indices, and then here what I am checking. So here instead of saying this length as a j plus 1, here instead of writing this one as a j plus 1, because this is only valid for the first subarray, what I will do, I will keep track of the length as well, and initialize this length with 0, and then whenever the value of the current or of the subarray is equal to mask, so in that case I will simply take answer, maximum of answer, comma length. So instead of j plus 1, and because in that case you have to use two pointers, that is the starting index of the subarray and the ending index of the subarray. So that's why I have another variable length which is equal to 0, and then I am checking if a of j and mask is not equal to a of j. Then what does it mean? It means it has some bit set which is not required. So this is the case that we are checking. This case, yeah, this case I am checking, and if that is the case, then we have to start a new subarray. If that is the case, then we have to start a new subarray. So start a new subarray which is current, for which the current is equal to 0 and the length is equal to 0, and then continue. Take me to the next index from where I will start a new subarray. And here, okay, let me just explain you this thing, AI and mask. So let's say this is the value of mask. The value of mask, it is equal to 2 power 4, 4 minus 1, which is, let's say, 2 leading zeros, and 4 times 1, 15, the binary representation of 15. And let's say the value of a of j, it is equal to 1, 0, 1, 1, 1, and 1. And what if I take AND? What if I take AND of these two values? So if I take a AND of these two values, if I take a AND of these two values, then it is equal to 0. Not 0, but yeah, it is equal to 0 0 at these positions, and then at these positions I have 1, and this value which is not equal to a of j, and if it is not equal to a of j, if and value is not equal to a of j, then it means it has some set bit, it has some bit set which is not required, which is out of this mask. So that's why we cannot add a of j in the previous subarray, we cannot extend the previous subarray, and then we have to start a new subarray. So that's why current and length is equal to 0. And if that is not the case, then I can include the element in the subarray, that is a current or a of j, and increase the length, and whenever the value of current is equal to mask, whenever it is equal to the required mask, then I will simply update the answer, and finally I will return this answer. So return answer, and the time complexity, 30 iteration of this outer loop and n iteration of this inner loop. So it is 30 into n. So successfully submitted. So the fourth problem, count valid pairs. In this problem, you will be given two arrays A and B, where array A has n elements and array B has m elements, and your task is to count the number of valid pairs I comma j, where I is in the range from 1 to n and 1 base indexing, and j is in the range from 1 to m, where m is the size of array B and n is the size of array A. And a pair I comma j is valid when the GCD of A of I and B of j is not divisible by any element in either array A or array B. So let's see how we can solve this problem. So for this sample input, this is array A, then array B, and the number of valid pairs, is 7, and these are the indices of the valid pairs, and basically 7, and their GCD is equal to 1, and 1 is not divisible by any element of these array, either A or B. So in this problem, you have to think in a prime factorization. For every integer, things in a terms of a prime factorization, and GCD of A comma B. Let's say GCD of A comma B, the greatest common divisor of A comma B. It is always less than or equal to minimum of A comma B. Let's say GCD of 5 comma 15. So here in this case, the GCD of 5 comma 15, which is equal to 5. and GCD of let's say 10 comma 17. So in this case 10 comma 17, their GCD is 1, and you can think in terms of a prime factorization. So this 5 can be written as 5 into 5 into 1, and this can be written as 3 into 5. So the greatest common divisor, the greatest multiple, so 5, and here we have this 5. So that's why the GCD is 5, and GCD of a comma b, GCD of a comma b is always less than or equal to minimum of a comma b. There is an exceptional case, that is a GCD of 0 comma x. So in this case 0 is divisible by every number, so that's why in this case GCD of 0 comma x, it is equal to x. So this is an exceptional case, but it is explicitly mentioned in the problem statement in the constraint part that all the values of ai is less than or equal to n and greater than or equal to 1, and similarly b is in the range from 1 to m, and then here are the number of elements, which is up to 10 power 5, 4 into 10 power 5. So let's see how we can solve this problem. So no element is equal to 0, so you don't need to worry about this case 0 comma x. So then what is the maximum GCD that we can have? So a of I is in the range is up to n only, where n is the size of array itself, and b is up to m only, where m is the size of array b. So tell me, what is the maximum GCD? So the maximum GCD that we can have is maximum of n comma n comma m. This is the maximum GCD possible, and even it is not, but this is a safer side, n comma n. It is not possible to have a GCD as n or a GCD as m, but we can take this limit as the maximum. So let's say max is equal to maximum of n comma m. So just iterate over all the possible values of GCD and find the number of pairs. Find the number of pairs which have this GCD. So g is equal to 1, and it goes till mx, and for every g for every g I will find number of pairs with GCD with a GCD equal to g. So let's see how we can find the number of pairs for all the values of g. So let me write some example here. So in this case, so first of all I will define a function. Let's say f of I is equal to number of pairs for which number of pairs of I comma j for which GCD is I is equal to I. So can I say this thing f of I, this is a state, and can I say this thing f of I is equal to count 1 of I, the number of occurrences of multiple of I, multiplied by count 2 of I. So the number of occurrences of a multiple of I in array 2. So let me just write it here in this way. So count of 1 of I, it is equal to number of multiple of I, multiples multiples of I in integer array, multiples of I in integer array A, and count 2 of I, it is equal to number of multiples of I in array B, in integer array B. Cool. So this is the recurrence relation, count of I, count 1 of I multiplied by count 2 of I. So let me just write some example here. So let's say A is equal to 6, and I am writing the numbers in terms of prime factorization. Let's say the first element which has prime factorization 3 into 2, and let's say 3 into 3, which is 9, another element 9, and let's say the another element which is again 3 into 2, 6. Then in array b, let's say the first element that we have is 3 into 5, and the next element, let's say 3 into 7, and I'm writing in terms of a prime factorization, and let's say 3 into 11. So now how many pairs are there for which the GCD is, let's say 3. So let's say the value of I is equal to 3. So f of 3, how many pairs are there? How many pairs are there for which the GCD is equal to 3? So the number of multiples of 3 in array A, which is equal to CNT1 of 3, it is equal to 3 multiples, and similarly CNT2, which is with CNT2 of 3, which is also equal to 3 multiples of 3 in array B. So all the pairs, that is a GCD of this element and this element, this element and this element, is equal to 3. Here the greatest common divisor, here we have 3, and GCD of every pair, GCD here, the GCD of every pair, this element and this element, GCD is 3. Then this element, first element of array A and the second element also having GCD 3. Then first element and the last element of array B is also having GCD 3. So all the pairs are having GCD 3. So can I say this thing? It is equal to CNT1 of I multiplied by CNT2 of I. That is the number of ways to select one element from array A multiplied by the number of ways to select one element from array B. So f of 3, which is equal to 3 into 3. But this is not the correct recurrence relation. And why is it so? So let's say instead of this term 3 into 7, we have a term 3 into 7 into 3. So let's say this is the prime factorization of a number. So if this is the prime factorization of number, then you cannot say f of 3 is equal to 3 multiplied by 3. Now all the pairs does not have a GCD as 3. Consider this case. GCD of these two elements, GCD of 3 into 3, comma 3 into 3 multiplied by 7. So here in this case, the greatest common divisor is the product of common prime factors, which is 3 into 3, and yeah, this is a GCD. So this is not the correct recurrence relation. So then what is the correct recurrence relation? So f of I, which is equal to number of multiple of I in array A multiplied by number of multiple of I in array B, and minus, we have to subtract something. Subtract the contribution of its multiple. So the first multiple of I, which is 2i, so it is very similar to the prime C. So f of 2i. So this is the first multiple of I, minus f of 3i, and minus f of 4i, because there might be a case when the pairs are having GCD other than I, which is the multiple of I. So for example in this case, it is equal to 3 into 3, which is, so here in this case, here in this case, both the numbers are a multiple of 3, but their GCD is not equal to 3. Their GCD is equal to some multiple of 3. So that's why from here I have to subtract the contribution of its multiple. So minus 4i and so on up till f of I, f of lambda into I. Lambda into I is the largest multiple. So this is the largest multiple, which is less than the range. So which is less than or equal to max, because this is the maximum possible GCD we can have. We can have a maximum possible GCD as the max. So yes, this is the correct recurrence relation. And since the problem is having overlapping subproblem, to compute the value of f of I need to know the value of f of 2i and f of 3i and f of 4i. So the overlapping subproblem, so we can use a dynamic programming. So yeah, this is all about the explanation part. Now let me just show you the implementation. And once you get this value of f of I, that is number of pairs for which GCD is I, then just simply check whether this element I in the array is present or not. If this element I is present, then it cannot be your answer. This GCD cannot be your answer because I is divisible by itself. So if integer I is not present in any array, either A or B, in any array, then add the contribution of I, that is answer, plus equal to f of I. Add the contribution of f of I in your answer, because this I is not divisible by any integer. This I is not divisible by any integer. So this I can form a valid pair. So answer plus equal to f of I. So for this thing, I need to have some kind of data structure to check whether it is present or not. So here I am using visited array. So visited array. So if visited of I is equal to 0, then it means I is not present in any array. So in that case, I can add its contribution in my answer. So now let me just show you the implementation. So the maximum GCD possible is maximum of n comma m, because all the elements in array A is in the range from 1 to n. All the elements of array B is in the range from 1 to m. And then here I have declared a vector visited of size m plus 1. Then here I am having variable count 1 to store the frequency of multiples of I, and count 2 to store the frequency of multiples of I in array B. And for a frequency purpose, here I am having f1 for array A and f2 for array B. So first I am storing the frequency of all the elements from index 0 to n minus 1, and then I am iterating over all the integers from 1 to n, because the possible values of element is 1 to n. And then I am checking if the ith integer has some frequency that it is present in array A, then I will mark this integer as a visited, and count of I is equal to f1 of I. And then I am iterating over all its multiple, that is 2i, then 3i, and 4i, and so on, while it is less than n. And then I am marking their multiples as visited, their multiples as visited, and storing their frequency f1 of j in the count 1 of I. Count 1 of I will store the frequency of multiples of I. So that's why first I have initialized this count to 1 of I as f1 of I, because number itself is a multiple of it, and then I iterate over its multiple, and add the frequency of their multiple. Cool. Then I'm doing the same thing for array B, and similarly we have f2 for a frequency, then count 2 for a frequency of multiples of I, and then here I am using the same visited array, because it must not be present in any array, either in A or in B. Here it is mentioned in the problem statement that GCD of A of I and B of I must not divisible by any element of either array A or array B. So then here I am having a DP vector of size m plus 1 and initializing answer with 0. Then I iterate over all the values from max to 1. So the maximum possible GCD and up to 1. And here I am iterating from the larger values to the smaller values, because to compute the DP, to compute the value of DP of I, to compute the value of DP of I, we must know the f of 2I, that is to compute f of I, we must know f of 2I, then f of 3I, and f of 4I. That's why from the larger values to the smaller values. And yeah, dp of I, it is equal to cnt1 of I multiplied by cnt2 of I. Then iterate over its multiple and subtract the contribution of its multiple. And if this element I is not present in the array, if this element I is not present in the array either in A or in B, then simply add its contribution in your answer. So this is the complete solution. Now let me just try to submit it. Cool, successfully submitted. And the time complexity is very similar to the time complexity of a sieve of Eratosthenes to build a prime sieve, which is n. Basically, it is a log into log of n. So log into log of n base 2. This is the time complexity, and we have another array b, and we are doing the same thing. So n plus this thing, n multiplied by this term, and plus m log of log base m, log m base 2, and multiplied by log base 2. So yeah, this is the time complexity, and the space complexity is also linear, as it is equal to maximum of n comma n, maximum of n comma n. So these are all the 4 solutions of last weekly contest 116, and you can find the solution in the description, and I will attach the link of all these solutions in the description, so make sure to check that out. And also write your feedbacks in the comment. It would help me to improve the upcoming sessions and upcoming weekly analysis. So thank you so much for watching this video, and have a good day.